In this lecture, we're going to talk about keto to enol tautomerization. So I'm sure I just gave everybody a mouthful. So let's go ahead and capture that. The reaction is keto dash enol tautomerization. Tautomerization. Okay, let's start by just kind of clarifying. This is very important. And even though I promised we'd be talking more about alkynes, let's also clarify that as of yet, this has no alkynes. So this is going to be like a tutorial related to keto to enol tautomerization, but just know it's coming. Its relevance to this exam material is coming, but it's not apparent just yet. Okay, so let's first define the last term, which is tautomerization. This is an isomerization or an isomerism. First of all, isomerization or an isomerism, which is the starting and final have the same molecular formulas. Okay, so let me just start by saying that this is a rearrangement of sorts. We're going to take our molecules and rearrange all the elements, but we're not going to add any elements. We're not going to take away elements. Same elements in and out. So it's an isomerization or an isomerism where the structures differ in the position of ... primarily hydrogen atoms. So this is kind of like constitutional isomers where only hydrogen atoms move. Now, if we're just moving hydrogens, it's hard to do things. So there's a second component. It's just tautomerization is typically specified as being an isomerization involving only hydrogen atoms, but it's not just hydrogen atoms. It's secondly pi bonds or double bonds within systems. Okay, so keto to enol is an example of one tautomerization, where tautomerization is a process or isomerism that's broadly hydrogens moving and double bonds moving. Okay, so here's the keto and the enol. Keto, this is short for carbonyl. And keto comes from like ketone-like. But it works for aldehydes. It works for any carbonyl. Okay, carbonyl is what keto stands for, short for ketone, I guess. Now, enol, and let's just draw a picture of this. Enol is alkene alcohol. Alkene alcohol. So enol is pronounced with a hard E. Enol, not enol. It's enol. I know it's kind of weird, but this is what chemists do. They put en at the beginning of a word and they say it's en. Okay, cool. So we have enol, alkene alcohol. Now what this looks like is we have an alkene and then directly on it is an alcohol, alkene alcohol. So alcohol directly on an alkene. Okay, so let's just do a quick test. Label the following as keto or enol. Keto or enol. So this, we have this, we have this, we have this. Okay, there's a few examples. All right, so first of all, we would label this as enol. It has the sort of alkene alcohol, and this similarly is enol. But the others have the carbonyl framework. And I guess I'm not going to highlight the carbons on either side of my ketone up here. It's just a carbonyl, a carbonyl. So those would be keto. Okay. Now similarly, and I should also include an aldehyde, shouldn't I? And I'm going to emphasize that it's an aldehyde. That is also a keto. And you're like, well, isn't it an aldo? No, aldo's something else, it turns out. So we'll call it a keto. Okay, so why are we learning this? Keto and enol tautomerization. Well, it's because it's there's a very important equilibrium that we all should be aware of in exceedingly good detail. I want, if I do this lecture right, I want to create an alarm in your mind that every time you see an enol, you want to cross it out for the most part and draw it as its keto isomer. So we have enol and keto with an equilibrium constant that in this orientation is exceedingly greater than 1. That is, the enol is favored at equilibrium. Okay. That is to say that if I have this structure, I want you to recognize, first of all, that it's an enol, and then say to yourself, must convert to keto. Must convert to keto. So you could draw favorable equilibrium arrows towards the right, towards products, and we're going to draw the keto form. Okay? Now, there are a few tricks for converting an enol to a keto that make this easy. We're actually going to save the mechanism for later in the semester. So the mechanism, it turns out, is just related to carbonyls a little bit more closely. So rather, at this point, I just wanted make it so you guys can just see these things and be like, ooh, I got to convert that to a keto or something. Turns out the reaction is catalyzed under acid or basic conditions. So as soon as you form an enol, if there's a hint of acid or a hint of base, it spontaneously goes right on over to the enol form, often without us noticing these things. It's very hard to like detect enol content by NMR unless there's something that we've done to the equilibrium constant to make it favor the enol form. So we must convert this. We must convert enols to the keto form when we see them. So one way of doing this is to recognize that an enol form, or the keto form, has a carbon-oxygen double bond. The keto form has the carbon-oxygen double bond, and the hydrogen has moved over. If you want me to trace elements, I can. There's my hydrogen with its single bond, and then my pi bond moved from here to here. Okay, so that's one approach. I think that's very helpful to see when you're considering the equilibrium going towards the keto form. Alternatively, we could practice crossing out. I'm going to do this with red. I'm going to have an intermediary structure so you can see what happened to ultimately give rise to this carbonyl. Okay, so because of bond line structures, all I have to do, I said I was going to do it in the middle, to get from the enol to the keto, is I'm going to cross out the carbon-carbon double bond, cross out the oxygen-hydrogen single bond, and add a carbon-oxygen double bond. So cross those out, and I'm at my keto form of my molecule. Okay, so let me practice this a little bit. Let's go ahead and draw a bunch of enols. So I'm going to consider this structure. 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 Okay. So I probably should have arranged these so I could actually fit them on the same line. I might do that really quick. You're probably writing this stuff down. So I'm just going to slide this over, slide these two over, get this up here. Okay. I'm going to draw favorable equilibrium arrows going from the enol content to the keto content, and you could practice this. So I first recognize where my enol is, and then I could cross out the carbon-carbon double bond, cross out the oxygen-hydrogen single bond, add a carbon-oxygen double bond. I could do that in every case, but let's just go one at a time. Contextual differentiation improves learning. So let's go ahead and go through the entire step as opposed to assembly lining this thing. But that's the first keto form. And you're like, wait, isn't that an amide or something? And I would say it's actually a lactam. But anyway, this molecule is just a carbonyl that's been drawn as its enol isomer originally. And we could have the hydrogen from the enol move down. But we don't have to draw that. We don't have to draw the enol hydrogen because this has just doesn't have to be drawn due to bond line structures. Okay, so let's go here and we'll draw our enol form or our keto form again. Now, how did I do that? I went a little fast, sorry. There's my enol content, my enol structure, excuse me. Go cross out the carbon-carbon double bond, add an oxygen-carbon double bond, cross out an oxygen-hydrogen single bond, and then I get the product. Now I can do the same thing over here. I've got this carbonyl trying to throw you off in this third structure, but just focus on the enol. Everything else stays the same. So everything else stays the same. This carbonyl is good. I'm going to add a carbonyl down here. Now we come over here. We're going on, oh, wait. Fourth one was a trick. Okay, in this fourth one, what we see is that the double bond has moved. See. So this structure is fine, okay? This structure is fine. This is not an enol. The alkene is not directly on the enol. It would have to be over here, but it's not. It's not drawn that way. So there's no keto form here because we didn't start with an enol. We actually started with a different alcohol called an allyl alcohol, which I'll just say those words because that'll be the topic that we talk about at the beginning of the next module. Okay, anyway, but it's not an enol. It's different. Okay, now over here, this last example, we've got a nitrogen. Actually, that counts. That counts. The carbon-nitrogen double bond can be rearranged to make a carbon-oxygen double bond, which is better. Carbon-oxygen bonds are better. Cross out here, carbon-oxygen double bond, cross out carbon-nitrogen single bond, and we get to a structure where the nitrogen now has two hydrogens and the oxygen has a double bond. Okay, and that's just like an amide or something. So I want us to get good at drawing and converting enols to keto forms. Now, the reason why is going to be, we'll just save it for next time. We'll have this be a separate video. But the reason why has to do with the hydration of alkynes, because we'll actually, if we add H2O, put an H on one side and OH on the other, we actually form an enol, which then gives rise to a carbonyl. So you don't do dihydration of alkynes, you just do monohydration and then you tautomerize. Okay, anyway, I'll save that for next time. So until then, we'll see you later.